Today we're going to talk about hyperplanes. So a hyperplane represents a system of equations in a space. So for an n space, so of any degree, of any dimension, a hyperplane will have n minus 1 dimensions. So for example, a hyperplane in a space of degree 3, so 3D space, is a plane, which is just 2D. So that can be applied to any dimension of space. A hyperplane can be represented by a point normal equation, which is given by the vector n dot vector r minus vector p naught, which is equal to 0, where p naught is the position vector of a point P on the hyperplane, r is the position vector of another point M on the hyperplane, so that can be any point, and n is a vector that is perpendicular to the hyperplane P with vector coordinates a, b. So this makes sense because if n is normal to the plane and r and p are on the plane, then the dot product should equal 0 because they are at 90 degrees to each other. So if we perform the dot product operation with n equals ab, p naught equals x naught y naught, which are just variables, and m equals xy, then we can create an equation ax plus by equals c. This is the general form of the line P through P naught, of the plane P through P naught. In this case, it would be a line because it's in 2 space. So that would be the general form of that line or the hyperplane in 2D through P naught and M. And this can be extrapolated for higher degree spaces. So there's an important formula that we need to know for distance. So first of all, the normal vector of a hyperplane is n, which is ab for 2D, or n abc for 3D, etc. A, b, and c are the coefficients of x, y, and z, respectively, in the general equation, general form. So the distance d between the point p naught, which is on the plane, is not on the plane, rather, and the plane ax plus by plus cz plus d equals 0 is distance equals ax naught plus by naught plus cz naught plus d, the absolute value of that, all over square root of a squared plus b squared plus c squared. So just remember that the d term is included in the numerator but not in the denominator. So procedure for finding distance. First, we want to find the normal vector to the plane using the coefficients of the terms of the plane equation. So again, that comes from the general form. Then we want to create a line which is parallel to the normal vector that does pass through the point. So use the point form, point coordinates plus scalar x, normal vector, scalar times normal vector rather. And then we want to set up a system with x, y, and z in the equations for this line, replace x, y, and z in the equation of the plane to find the intersection point between the line and the plane, solve for the scalar, and plug back into x, y, z equations to find the coordinates of the point of the plane, and then finally use the distance formula to find the distance from the point to the plane. So it's a bit convoluted, but basically you just find that normal vector, create a line parallel to the normal vector, that goes through the point, and set up a system and solve the system essentially, and then use the distance formula. So we'll go over an example of that right now. So finding the distance between the point m1, negative 4, 3, and the plane x minus y plus 2z equals negative 1. And then just for an extra example, we're going to find the point normal equation for a hyperplane which lies on 3 points, or on which 3 points lie, rather. Okay, so we're going to start with this example. And then you can find the other example in the description, as always. So, the first step is to find the normal line. So if we have our line here, which is x minus y plus 2z equals -1. Then we can use the, sorry, I'll just point it out here. So we can use the coefficients here. So that 1, -1, and 2. And we will find that normal from those coefficients. So we can say that the normal is equal to 1, -1, and 2, just from those coefficients again. And that is in vector form. So then we want to find a line L. So this is moving on to our second step. Find a line L through P and M parallel to N. So we have L equals 1, -4, 3 plus T 1, -1, 2. So that's just taking the point 1, -4, 3 and the normal vector and point plus the scalar times normal vector. And then we can set up equations. So we know for x, so x would be, let's box it here, 1 plus 1t, or just 1 plus t. Y would be -4 plus -t. So -4 minus t. And z would be 3 plus t, 2t. So then we have a system of equations here. Okay. So let's go back here. We've done our first 3 steps, and then we want to do our 4th step. So replace x, y, and z in the equation of the plane to find the intersection point. So use these equations here, which we just created, in the equation of the plane. So then P, we'd replace x, y, and z, would be equal to 1 plus t, 1 plus t minus -4 minus t plus 2, 3 plus 2t equals -1. Okay, so if we simplify, then we have 6t equals -12, so t equals -2. Okay, and so we can go ahead and solve for x, y, and z. So then x equals 1 minus, 1 plus -2, y equals -4 minus -2, and z equals 3 plus 2 times -2. So then x is -1, y is -2, and z is -1. So then we get our intersection point, which I'll label n, which is -1, -2, -1. So then once we have that, we can simply put it into our equation here. And find the distance. in fact, since we know our 2 points, all we have to do is find the difference between the 2 points. So we can do, we'll call it, well, just mn equals, oops, n minus m, which is, okay, so -1, -2, -1 minus, we have for m here, 1, -4, 3. And that will give us, so -1 minus 1 is -2. -2 minus -4 is 2. -1 minus 3 is -2. Okay, that works out for us. And just make sure that's correct. Okay. No. I made a mistake. Sorry. -1 minus minus 3 is in fact -4. Okay. So then we can simply use length formula. So mn equals square root of -2 squared plus 2 squared plus -4 squared, which is equal to root 4 plus 4 plus 16, so root 24 simplifies to 2 root 6 if you need to simplify it. So yeah, that's how we find the distance. We can also use the formula if we need to, I suppose. But that's one way to find the distance. So we found the point at which passes through, and then the normal line passes through, and then we found the distance from that point to our point M. And that is it for this video. Thank you again to Loom and Google Keep, and as well to my professors. And look at the description for the annotated version of this, as well as the extra example and the PowerPoint as well. And thank you for watching. I hope this helped.